So let's say on our good old XY plane, we have a 1 nanocoulomb point charge at x equals 2 meters. So we already know that this point charge is going to be creating an E field radially in all directions. And if we were to take a imaginary probe and just pick certain points in this map of ours, so let's say we were looking like right here, we're so close to this that the electric field intensity is probably going to be pretty extreme, right? We're going to be able to feel it like a very high magnitude. Meanwhile, if we're a million miles away over here, like we might not even be able to tell if there's a point charge over here because we're just so far away that the electric field intensity has dropped off so much. So the specific question that I want to go over today from the exam is asking us to first find the potential at two different points, point A at y equals 2 meters and point B at y equals 1 meters. So after we find the potential at these 2 points, it specifically also wants to know the potential difference VA minus VB. So before we can do that though, you need to understand potential itself. So as I said earlier, we're going to be experiencing this electric field intensity differently depending on where on the map we are. So if I'm over here at point B, so like let's imagine we have a 1 nanocoulomb charge here. This isn't actually there, this is just for an example. I'm going to be experiencing this field line, so like this RB going straight through this point. Now, at point A, it's slightly different because it's higher, right? It's a different position. So it's going to be experiencing, the amount of energy this is seeing is going to be different due to the distance between this point and our point charge here compared to if our test charge over at point B, the distances are different, right? So we have two different points of observation, is how I like to think of it, and each one is going to be experiencing the intensity differently for that point charge. Now, potential difference, the meat and potatoes of this question, VA minus VB. This is essentially saying, it's asking us to find a scalar. It's asking us to find how much work per unit charge would it take to move our imaginary 1 nanocoulomb from point B over to point A while being influenced by this E field. So that's a lot of like magic talk, right? So I like to think of it, if you like, just imagine it's mechanics all over again, because mechanical potential energy I feel like makes more sense than energy and work electrically. So if we're specifically talking about VA minus VB, this would be VB down here, and up here would be our VA. We're starting at the bottom of the hill, and like where our imaginary 1 nanocoulomb charge. Now it's going to take us work to go from point B to point A because we have, in this case, this is just this position on the graph. We're not actually going uphill, but we do have this point charge here, which kind of acts as our hill, right? So we're putting in work to increase our potential energy, and we're putting in in this situation, it's putting in mechanical work to put in to get mechanical potential energy. Here, it would be some sort of power source, battery, putting in work to chemically move our 1 nanocoulomb charge from point B to A. So we know conceptually that there's going to be some work done for this potential difference, but how do we actually calculate what this is? Now, this is actually easy because we know that this is the field is being generated by a 1 nanocoulomb charge, and we know the position of that charge. So the reason why that makes it easy is because we have a nice equation for our difference, and that is the negative line integral of E dot dl. So we already know that the electric field intensity from our point charge is going to be our 1 over 4 pi epsilon naught constant, Q r squared. Now, we like I said, this is the reason why this is easy. We know what this E field's being caused by. We know the charge of it, and because we know the XY coordinates of our points, we're able to get our R values for this pretty easily. Then our DL, we're integrating across for this. It's gonna be here. So we're going, this is our DL, this is our line, our integrating line going from B to A. So I won't waste time integrating this, but just know it's in reverse integral, negative integral. So like I said, if we're all the way out in infinity, we're not going to even experiencing that. So instead of going from R to infinity, negative line integral goes from infinity to R. So won't waste time solving this. I've done this before. Constants all stay the same, and then we're left with, so this R squared is just in reference to this point charge at like one spot. So we actually need a, think of this as the difference between them, because we're not just looking at like VA or VB, we're looking at the potential difference, right? So this part is important. We can just say, because we know the coordinates here, what is A is the top one, so let's be like 2 meters squared, 2 meters squared, 4 and 4 is 8, 1 meter squared, 2 meters squared, and that is 4 plus 1, 5. So we know this, it's just 1 nanocoulomb, or 1 times 10 to the negative 9th coulombs. This is a constant. We know this is, means use this all the time. It's 9 times 10 to the 9th. And then we have our 1 over square root 8 meters and 1 over square root 5 meters. So cancel, cancel, and then we're left with 9 over square root 8 minus 1 over square root 5 volts for our potential difference for VA minus VB. Now, what actually is this? This isn't, like I said, we're putting in work to get potential energy, right? But this isn't total work. This would be the work per unit charge to go from this difference to this difference, right? So this is work per unit charge. Part B, knowing this makes part B super easy, because this yes, it's voltage, but you need to understand what that actually, the concept behind what this is, because part B is asking us what is, like, let's see, part B, how much work would be done by an external agent in moving a 1 nanocoulomb test charge from point B to A. Well, that's quite convenient. So I already said this earlier, but in real life, this external agent would be like a battery or something. Like if we thought of this as a capacitor and we're moving from B to A, we're not just going to flow from this magically. We're going to need our external agent. My camera is getting out of focus. I hope it's not like that the whole video. We're going to need an external agent, and that is probably going to be like a battery or something, power supply, anything like that. This is actually doing the work to move from this plate to that plate, right? So if this is work per unit charge, total work is going to equal our charge times this that we already found. Easy, right? Because the question specifically says 1 nanocoulomb test charge. So that is a very convenient number. So there's just 1. And then we multiply this by our 9. What was it? 1 over square root 8 or square root 5 volts. And then this just become, we could just say this -9, we'll just call this nano, and we have coulombs and volts. So now we have 9. We can, if we just say the -9, 10 to the -9 is nano, we'll just say this is our original potential difference answer, but now it is work. So it's nanojoules from these constants. So this is the total work it is going to take to go from point B to point A.